Okay, so welcome to our next unit. Let me just get my pen going here. This is oxidation and reduction reactions, and this is going to be called REDOX for short, and this is page number 93 in your notebook. All right, so let's go on to our next slide. All right, so what are redox reactions? So redox reactions are called oxidation and reduction reactions, right? So we have ox, right? That's the ox in redox, and RED, so reduction and oxidation. And the two reactions occur at the same time. Sometimes you might see the word simultaneously, because that's a big word, isn't it? All right, and it's a transfer or a shift of electrons, of valence electrons. Right, so it's a transfer or shift of electrons, right? So basically, we're going to be looking at loss and gain of electrons in a chemical reaction. So we're going to start off with reduction, right? So reduction is when an element gains electrons. So remember, electrons are a -1 charge. If you're adding a -1 charge, the oxidation number goes down, right? Just like if I take a number and I add a -1, the number goes down on the number line. And the charge is reduced. Remember, the oxidation number, some examples of oxidation numbers are on your periodic table in the upper right-hand corner. You should have your periodic table, reference table, ready to look at for this set of notes. All right, so now what is oxidation? So now this is very yin and yang in chemistry. So this is the exact opposite of reduction. So when an element loses electrons, remember when you're losing electrons, right? An electron is a -1 charge. So subtracting a -1 in this case. And so that means that the oxidation number goes up, right? So the oxidation goes up, a big ox. I like to remember that an ox is a big animal, big ox. And the oxidation number goes down for reduction, right? Reducing means going down. And so our charge then is increased. The oxidation number gets bigger, right? So the oxidation number goes up in oxidation. The oxidation number goes down in reduction. And we have a handy dandy way of figuring this out or helping us remember, and that's Leo the lion says grr. So which is why I have a lion on my desk. His name is Leo, and Leo the lion says grr. And I'm sure Mrs. Mitiga also has a lion that says grr. And so here's a lion. So Leo is the name of our lion. Hello, Leo. And that stands for lose electrons is oxidation. So lose electrons is oxidation. The oxidation number goes up. Now we have gain electrons, grr. Gain electrons is reduction, grr. And the oxidation number goes down, reduced. So why do substances undergo these redox, oxidation, reduction reactions? To achieve 8 valence electrons, remember that is called a stable or full octet, like a noble gas, group 18 on our periodic table, right? So to achieve an 8 valence electrons. So some common examples of redox reactions are bleaching, right? So if you get some Clorox bleach on something, right, that's an oxidation reduction reaction. Combustion, right, which is burn. So from our organic units, right, we have 2 products formed in combustion, carbon dioxide and water produced. Corrosion is an example of a redox reaction. So when metals corrode, that's called that's oxidation reduction. Tarnish, right? So tarnish is usually what we say when silver corrodes. Rust is what we call when iron corrodes. And what kinds of things can accelerate how fast, right, the rate of these corrosions? right? How do we get a metal iron car to rust or corrode the fastest? Water, air, acids, and salts, right? So these are going to be factors that accelerate the rate of this corrosion, the rate of these oxidation and reduction reactions. So before we get into the reactions themselves, we have to understand what an oxidation number is. So the oxidation numbers are the positive and negative charges formed when an atom gains or loses that negatively one charged electron, right? And they're all located on the periodic table. And we usually put the oxidation number in the upper right-hand corner. So we have positive oxidation numbers. So that indicates an atom has lost electrons. It's positive because the protons that are positive no longer equal the electrons that are negative. We have more protons than electrons, you have a positive oxidation number. Negative oxidation numbers indicate that an atom has gained electrons because we're adding a -1, right? And again, the protons that are positive do not equal the electrons that are negative. If you add more electrons, we have more negative charge, so therefore a negative oxidation number when you're adding electrons. So how do we assign oxidation numbers? So in some cases, we're going to have to figure these out mathematically, but we also need to use our periodic table. All right, so a free element, that means an element that is not combined, means there's no electron transfer. It means not in a compound. The oxidation number is 0. Any element by itself has an oxidation state of 0. That means that the protons that are positive equal the electrons that are negative, and there's no loss or gain of electrons. So we have monatomic free elements and diatomic free elements. Oops, let me go backwards, hold on. So a monatomic free element, like if I see iron by itself, I would say that has an oxidation state of 0. Or let's say I have aluminum, right? Aluminum all by itself, oxidation state of 0. Now we have our diatomic, right? These are the elements that exist bonded together, 2 of the same element bonded together, still an element, not a compound. And I like to call these our Brinkelhoff, or we can sometimes call them Hoff-Brinkel. So Brinkelhoff or Hoff-Brinkel, or 7-Up, right? They form the number 7 using group 17 and then group 15, 16, 17, nitrogen, oxygen, fluorine, and then down to iodine, and then up is our hydrogen up at the top. These exist bonded together. So Br2, I2, Cl2, H2, O2, and F2. So if you see oxygen in a reaction, then the oxidation state is 0. It is uncombined. Same thing if I just see hydrogen, right? It's an element, not a compound. So that means that the oxidation state is 0. Right, so now let's get into compounds. So now when we make a chemical compound, electrons are lost or gained or shared, and the sum of those oxidation numbers must equal 0 because all compounds are neutral. So for example, with magnesium bromide. All right, so now magnesium bromide, how do I figure out the oxidation numbers of magnesium bromide? Well, first I'm going to go to my periodic table and I'm going to find magnesium. Magnesium is in group 2 of the periodic table. So I'm just going to write that over here. So that's group number 2. And all of the elements in group number 2 have a positive 2 charge. That's a positive 2 oxidation state. That means magnesium loses 2 electrons. And here I have bromine. I look on my periodic table. And on the periodic table, bromine has more than 1 charge, but only one of them is negative. If I have a positive charge, I have to have an equal amount of negative charge to balance that. So each of these bromines is a -1 charge, right? Because 2 -1s is going to balance out that positive 2. So that means that my bromine is going to gain electrons, each bromine gains 1 electron. So I have 2 bromines that each gain 1 electron, right? So we have a loss and gain simultaneously when magnesium and bromine get together, right? And which one? Leo the lion says Gur, right? So which one loses electrons? Magnesium, then we'd say is oxidized, and then gain electrons, Gur, is reduction. So we say that that is going to be reduced. So now when we're assigning oxidation numbers, we have monatomic ions. And the oxidation number is going to be equal to whatever their ionic charge would be. So we're going to look on our periodic table. Our group 1 metals, right? So starting with lithium, sodium, potassium, rubidium, cesium, and so on. They lose 1 electron. They have a positive 1 charge. Always, no exceptions. And group 2 metals always lose 2 electrons and have a positive 2 charge. Now our group 17, our halides, are going to be most of the time -1. So I'm just going to write down here, mostly -1 if they're listed, and most obviously if they're listed last in a compound. If it's in the middle of a compound, then we're going to have to use a little bit of math to figure that out, which we're going to get into very shortly. All right, our polyatomic ions, if you recall, those are listed on table E. It's a group of elements that are bound together and have an overall charge, also listed on table E. The sum of the oxidation numbers of a polyatomic ion equals the overall shared charge, which is the charge listed on table E of your reference tables. So let's look at our first example, hydroxide. So hydroxide on table E is OH minus. That means that the oxygen plus the hydrogen has to equal up to -1. So I'm going to go to my periodic table and I look and I see oxygen can be -2. So I'm just going to do O, it's going to be -2. And my hydrogen says +1 or -1. So I need to figure out, is this hydrogen +1 or -1? So the oxygen is -2. The whole thing has to add up to a -1. So I have a -2 and I have plus what number is equal to a -1. We could do this with algebra and we can call that an X, right? Add 2, and that cancels. So our hydrogen is going to be equal to a +1, right? So if I have a +1 and a -2 added together, one of each, the overall charge is -1. So our hydrogen is going to be +1, right? And I used my known charge of oxygen on the periodic table. Now let's look at sulfate and ammonium, right? So sulfate is SO4 on table E. That means this whole thing has a -2 charge because that's what table E says. So I need to figure out the charge of sulfur and the charge of oxygen. So my first step is looking at table E. I know this whole thing has to add up to -2. Then I look at my periodic table. My periodic table tells me oxygen is -2. So I have a -2 for the oxygen, and I've got 4 of those oxygens. They each have a -2 charge. And that's going to be a total charge of -8 for the oxygen. So now my oxygen, right, this oxygen has a total charge of -8. This whole thing has to add up to -2. So then basically it's -8 plus what number equals a -2, right? Let's add 8 and let's add 8. And then that's going to be a +6. So then my oxygen is -2 and my sulfur is +6. Does that make sense over here? If I put a +6 in front of this sulfur, on top of this sulfur, a +6 plus 4 -2s, right? That's -8. So a -8 and a +6 equals a -2. Now our ammonium, right, is going to be NH4 with an overall charge of positive. And so I look at my periodic table. Nitrogen has a lot of charges listed on the periodic table, and so does, well, hydrogens can only be plus one or minus one. So in this case, I'm going to use the negative charge for nitrogen on the periodic table. And so I'm going to, let's see, if nitrogen's a -3, and I have 4 positive ones, does that equal +1? Yes. So then those are my charges for the ammonium. Or you can play around with the different numbers. But in general, since nitrogen has the higher electronegativity, it needs to have a negative charge. So if nitrogen is the negative charge, that's another reason why I can easily say for sure that the ammonium's hydrogen is going to be a positive. Now let's talk a little bit more about that hydrogen. So hydrogen uses a +1 charge. I know that's kind of hidden up there, so let me just click on that, +1 charge. For the most part, you can confidently say hydrogen's going to be a +1 most of the time. There are a couple of exceptions. Now the exceptions are hydrides, where it uses a -1 charge, because a hydride is with a group 1 or group 2 metal and hydrogen. So for example, with sodium and hydrogen, sodium is in group 1. The only possible charge for group 1 is +1. So hydrogen cannot also be a +1 because we have to have the numbers add up to a neutral charge of 0. We have to have a positive and a negative. So that's where we're going to get that -1. So then let's determine some oxidation numbers. So we have the element Au. So then we have just one element, and we have an oxidation state of 0 because it is neutral, because it's an element and it's uncombined. Our protons that are positive equal our electrons that are negative. So now here we have a compound. And let's do a little bit of review in here. This happens to be a covalent compound because I have 2 nonmetals. I need to figure out the oxidation states. So if I go to my rule above, hydrogen is going to be a +1. So here's my hydrogen being a +1. So I'm just going to do H is equal to +1. And our positive ions are usually listed first. Plus, sulfur has a higher electronegativity than hydrogen, so it's going to be a negative. So what will the negative charge of sulfur be? Sulfur has more than 1 charge on the periodic table. So I have 2 hydrogens that are each a +1. So then my total hydrogen charge is +2. So then if I split this molecule, that means that this 1 sulfur has to cancel out a +2. So it's going to be a -2. So the sulfur is equal to -2. Not sure why it made that little weird line. Now let's look at lithium oxide here. So I go to my periodic table. Lithium is +1 because group 1 can only be a +1. Now oxygen is usually a -2, but this is one of our exception to oxygen being -2. So this is going to be an exception to oxygen. So oxygen as -2, because lithium is in group 1 and group 1 is always +1. So if I have 2 positive ones, that means my total charge for lithium is +2. So if I split this molecule in half, this compound in half, if the metal side is equal to +2, then this side has to add up to -2. But I have 2 oxygens, so each one must be a -1 to add up to a -2. So this case, I have lithium is equal to +1, and then oxygen is going to be equal to -1. This is a peroxide, and this is pretty rare. You're probably not going to see this on the Regents exam, probably maybe not on a test in honors. I would definitely say to make sure you can do an oxygen exception rule with the peroxide, right? So hydrogen peroxide is another example where you would have oxygen being a -1 or sodium peroxide, right? So then those would be your exceptions to oxygen being -2. All right, one little last bit, we're at the bottom of page 97. We're going to look at, oops, S8, forgot about that one. So I have only one element. This is an element. And so the oxidation state is 0. All right, so we're going to go on to how do we recognize redox reactions, oxidation and reduction. So not all reactions are redox reactions. There has to be a change in the oxidation number in order for something to be classified as redox. So an oxidation number has to go up or go down, indicating the loss of electrons or gain of electrons. So reactions that are always redox, without fail, this is what I'm looking for in a multiple choice question, for example. Any reaction that transfers electrons, combustion, right? So then this is when we have an organic reaction that produces carbon dioxide and water. Single replacement, right? So I love to look for single replacement reactions. Remember, single replacement is element plus compound making new element and new compound. And decomposition or combination, and remember or we can call that sometimes synthesis. All right, so synthesis, decomposition, combustion, and single replacement are always redox. Reactions that are never redox, right? So these are types of reactions that we learned earlier in the year. Are double replacement reactions, right? So remember, double replacement reactions are compound 1 plus compound 2, and they rearrange themselves to make 2 new compounds. And then neutralization is a special kind of double replacement where we have an acid plus a base makes an ionic compound, a salt, and water as a product. So those are reactions that are never redox. So there's always a change in oxidation state in combustion. And there's always a change in oxidation state in single replacement, synthesis, decomposition. And there's never changes in oxidation states in a double replacement or a neutralization reaction. So the oxidation numbers stay the same from left side to right side. So in our next video, we will spend some more time on oxidation and reduction and rewriting those kinds of reactions and picking which ones are oxidation and reduction.